Morning, class.
Good morning, Mr. Lara.
How's everyone doing today? Today, we're learning about curvature. Who likes curves?
I do.
Great. To begin, let's imagine walking along a curved path. The rate at which the path is turning, or this little red thing, the rate at which this unit tangent vector changes directions is what we call curvature. Does anyone have any idea how we would calculate this?
Well, I know how to calculate the rate of change of a function. You can just take the first derivative.
Like how the derivative of position is velocity.
Yeah, but how does that help? Isn't curvature a little different than rate of change in position?
Yeah, you're correct. Curvature deals with the rate of change of the unit tangent vector along the curve. The rate at which this changes directions is called curvature. And we define it using the variable kappa or k. So essentially what we're calculating or concerned with is just how big this dt is right here, because the bigger the dt, the greater the curvature essentially, because if you add these two vectors together, you'll get something steeper like this by vector addition. On a straight line with this in mind, what do you guys think the curvature would be?
I guess the curvature would be 0 because the unit tangent vector t doesn't change direction at any point on the line.
What about a circle?
The curvature wouldn't be 0, but it would be constant. Around a circle, the unit tangent vector t is always turning at the same rate.
Great answer. K is not necessarily constant everywhere on a curve, but the greater the value of the curvature of K, the more curvy the curve is going to look, and so the more the unit tangent vector is turning. So here we have what we're given. Curvature, kappa, K, whatever you want to call it, is given by the magnitude of the vector dt over ds, ds being some arc length element. But we can rewrite this as, by the chain rule, dt over dt over, and we can rewrite ds over dt as just, we'll just write r prime. T equals the unit tangential vector, which can be found by just the first derivative of the curve over its magnitude.
I don't quite understand. I heard something about the radius of curvature. What's that?
Fit in a circle into this little nook of our curve right here. Let's see how good we could represent the curvature. It's nice. And for point Q over here, it's not that curvy, so we could just imagine a big old circle. It's got a bigger radius than the one we drew for point P. Another way of thinking about curvature is that just try putting a circle on it, and the inverse of the radius of this imaginary circle, you could use it to estimate the value of K.
Oh, that makes sense. I see how we can relate curvature to circles. Is this all we need to know about curvature?
Not so fast there, Owen. We actually have to consider the unit normal vector of this curve as well. And the unit normal vector is important because it points in the concave side of the curve. Concave meaning just the way in which t is turning. So it's real important to describe motion. Here on the board I have written the initial definition of the normal or principal unit normal vector, or the pun vector. It's equal to 1 over the curvature times dt ds. This formula states that n is parallel to dt, which means it's also perpendicular to t. So we would have a normal vector n as well as tangential vector t. Let's try plugging in our definition for kappa here. It's kind of low. So up here we have kappa is the magnitude of dt over ds times dt over ds. So makes sense that it's a unit vector as well. And since it's in the direction of dt, still makes sense that it is orthogonal to t. Alright, class, with everything in mind, who thinks they are ready to tackle this problem?
I think I know how to solve this. Okay, so first, to solve this problem, we have to find r prime, which is pretty easy. You just take the derivative with respect to t. And then to find t, it's going to be t is equal to r prime of t over the magnitude of r prime of t. So we all know how to find the magnitude. It's just going to be the square root of this squared plus this squared. So we have, and then that's going to become, okay, so this overall simplifies to a squared, which is just a. So our t is going to be equal to t over r prime of t. So again, to find t prime of t, we're just going to have to take the first derivative here with respect to lowercase t, which is going to give us sine t. And then to find t prime of t, or to find the magnitude of t prime of t over r prime of t, well, we already found the magnitude of r prime of t, so we're going to do the magnitude of t prime of t, which is negative cosine t squared plus negative sine of t squared over a, which we found previously. And then this is going to simplify to square root of 1, which is 1. So this is going to overall simplify to 1 over a, which is equal to our curvature.
Wait a second, Owen. I think that makes sense. We learned that the radius of curvature is the radius of the circle that fits inside the curve at that point. And the curvature that you found is 1 over a, or 1 over the radius of the circle.
That makes sense.
Very well done, Owen. Now, who thinks they can tackle the second one?
I can do it.
The first step is to find the first derivative of r of t. Now, in order to find t, I want to find r of t over the magnitude of r of t. Therefore, let's calculate the magnitude of r of t. That is, now we can plug this into our equation of 2t cosine of 2t. And that is our t value. So n is defined to be, as Mr. Lara said, dt over ds all over the magnitude of dt over ds. Let's use change. Multiply this by ds over dt. And then we get n is also equal to dt over dt over the magnitude of dt over dt. So let us find n. Taking the derivative of t, we get, and then we can find the magnitude of t, and then that would equate to, we get that equals to negative 2 cosine 2t, negative 2 sine 2t, all over 2, which simplifies to negative cosine 2t, and then negative sine 2t.
How to solve for curvature with a simple example and also find the tangent and normal vector But how does solving for curvature and these vectors apply in the real world? When can we use stuff like this?
So we can actually use the normal and tangential vectors of curve to describe the motion of, say, a particle in space. And these two are useful, but they are not enough. We actually need one more to completely grasp the entire motion of that particle in space. And that vector is called B, the binormal vector, unit binormal vector. It is binormal because it is the cross product of t and n, so it's perpendicular to both t and n. If you were to stick all three of them together, let's say this is the point P on some curve going like that, somewhere off to the side. We have, this is T, and this is N. And these three vectors create a right-handed frame, similar to the Z, X, Y, three-dimensional Cartesian coordinates that we're all familiar with working with, that moves along the curve and is really useful for describing motion along said curve. We can take the derivative of the binomial vector with respect to the arc length, and that's the same as, should we do that, which would give us dt ds cross n plus t cross dn ds. And what's cool about this is that this simplifies to 0 since dt ds points in the same direction as n, as we found earlier. And we're just left with t cross dn ds, which tells us that the derivative of the binomial vector with respect to arc length is orthogonal to the tangent vector. So I guess on the graph here we can just draw something like this. And since not only is it orthogonal to t, but it is also orthogonal to b, so this whole thing is just orthogonal to this entire plane made by these two vectors. Since dbds is orthogonal to this entire plane, bt, we can conclude that it's parallel to n. And a way we could represent this is that dbds is some scalar multiple of the n vector. And we can represent it using this formula, tau being torsion. Torsion, we get that it is equal to the dot product of those two vectors. Represents how twisty the curve is. Another way of thinking about it is like how, okay, so this binomial vector represents how we twist out of the plane made by t and n, and by taking its derivative with respect to the arc length, we were able to find some scalar value tau that represents just how much the twists, how much this curve twists, if that makes sense. Another way to think about it would be to just draw the plane. Another way to think about it would be that tau measures the rate at which this plane made by t and n rotates about t. All right, who's got the guts to take on torsion?
Put me in, coach. Okay, this example wants me to find the torsion for this 3-variable space curve, not a plane curve. So I know that t is a unit vector equal to r prime over the magnitude of r prime. So let me find that. And the magnitude of r prime t is equal to square root of 5. So t, the unit tangent vector, is going to equal 1 over root 5, negative 2 over root 5 sine t, and 2 over root 5 cosine t. The next thing to do is find n, the unit normal vector. Katrina already derived the chain rule for this. So we know that n is going to be equal to dt with respect to t over the magnitude of that vector. All right, so let me find that. 0, negative cosine t, negative sine t. Okay, now I have my t and my n, and I think that the next thing to do is to find the vector b, which is the binormal vector orthogonal to both of these vectors. B is going to be t cross n. So let me set up my I, j, k. My b is going to come out to 2 over root 5, 1 over root 5 sine t, and negative 1 over root 5 cosine t. Okay, now I have my t, my n, and my b. So those are enough vectors to describe the 3D motion of this space curve. But I want to find the torsion. And we know from what David taught that torsion is equal to negative dB over ds dotted with n. So I'm going to treat dB over ds as b prime, the magnitude of b prime over the magnitude of r prime, because we already derived that using the chain rule. So I think I can use negative dB over ds dotted with n. Let me do that next. To dot dB over ds with n, first I'm going to find b prime with respect b prime of t. That's going to be 0, 1 over square root of 5 cosine t, 1 over square root of 5 sine t. Let me dot this vector with n. When I dot two vectors, I should get a scalar product. These two terms factor out because of the trig identity, and I'm left with negative 1 over root 5. Now I'm going to divide that by the magnitude of r prime, which I found above is going to be root 5. That is the answer for dB over ds dot n. And the last thing I do is take the negative because of the formula for tau, torsion, equal to 1 over 5.
Okay, great job, class. Remember, there might be a few different equations that you might find out there that I didn't cover, but they all tackle the same thing, and they should reinforce the same concepts that I introduced in today's class.
Okay.